This video is about the transformations of trigonometric graphs. We will see four main function transformations at work, and function transformations that are very similar to transformations that we have seen on other functions, not just trigonometric functions. We'll start with the base function y equals sine of x, and one by one apply the different transformations. First, our a transformation, as I call it, is some constant multiplied to the function. If you remember transformations from earlier, this a transformation, a constant multiplied out front, executes some sort of vertical stretch or compress. Let's go right to some examples. Here is y equals sine of x, and now let's make an a transformation. Let's look at the graph of 2 times sine of x. And we do see that our graph has been vertically stretched by a factor of 2, where we had peaks at 1 and -1. Now we see them at +2, a peak at +2, a valley at -2. So each function value has now been multiplied by 2, and the result is stretching it by a factor of 2. We'll see it if we look at 3 times sine of x. Everything has been vertically stretched by a factor of 3. The positives have become more positive, the negative values have become more negative. Multiplying by a factor that is greater than 1 accomplishes this stretching, and if we multiplied by a factor that was between 0 and 1, we would see a vertical compress. We are multiplying by 0.4, so every function value is now 4/10 of what it originally was in the sine function, and the result is a graph that has been compressed. If we were to multiply by a negative number, the result will be, just like it was before, a reflection about the x-axis. Now with trig functions, it's difficult to see exactly what caused the change that we see right here. It is actually the same change as if we reflected about the y-axis, or if we reflect about the x-axis, it looks identical. It even looks identical to if we just shifted our graph one way by 180 degrees or opposite way by 180 degrees. So a few different transformations can all lead to the same effect. We'll explore those in more detail later on when we talk about some identities and even and odd functions, but for now, I want to point out that multiplying by a negative out front accomplishes a reflection about the x-axis as it has done with function transformations up to this point. If we multiply by a negative number, but not -1, we will see both of those changes. We will see a reflection about the x-axis, and we will see a stretch or compress. In this case, multiplying by -2.5, we have our reflection, and then vertically stretching by a factor of 2.5. When we're talking about trig functions specifically, we call that value of a the amplitude. On the graph, the amplitude is the distance from our midline to a peak or to a valley. The sine function goes between -1 and +1, but the amplitude is not a measure of that total difference, which would be a total difference of 2. It's actually half of that total difference. So a couple ways to look at it. One way would be look at our max to min, the complete range, which would be a total distance of 2, and then cut it in half is one way to find amplitude. Or the other way is that we just start off right at our midline and see how far it would be to go up to a peak or down to a valley. So sine, we know this is multiplied by 1, the amplitude is 1, and in our green graph, now we have an amplitude of 3, and we see that we are multiplying by a factor of 3. Next transformation we'll look at will be some constant added on to the end of the function, the d transformation. Back to our base function sine of x, if I look at the graph of sine of x plus 1, I see the entire graph has been shifted up 1 unit. Any point that I pick on the red graph, if I go up by 1 whole unit, I'll land on the green graph. Whether it's right on the middle line, or if it's a valley, up by 1 takes me to right there, or a peak up by 1 will take me there. Every single point on the red graph, if we increase it by 1, we will create the green graph. That is the result of this d transformation, some constant added on to the function. Here it is shifted up 3 units with a +3. If we subtract, we'll accomplish a downward shift. Here, the graph has been shifted down 2 units. Next transformation will be the B transformation, when we multiply directly to our variable inside of the function. Previously, this would accomplish some sort of horizontal stretch and compress, and also it worked opposite of what we might expect, whereas with the A transformation, when we saw a large number, our graph was stretched out larger, and a number between 0 and 1 would shrink the graph. It works opposite when we work directly on the variable. So a number that is greater than 1 is actually going to compress the graph together, while a number between 0 and 1, some decimal number, it's going to stretch the graph out. Here in maroon, we've got the base function sine of x, and in green, sine of 2x. Now we're on to this idea that it's doing some sort of horizontal compress, but we can see it a little bit more clearly. I'm going to go back and just look at 1.1x, and I'll increase this factor, this coefficient of x inside the function, to 1.2, and so on. And you can see that as that number increases, our graph is being compressed closer and closer to the origin. There we are at that sine of 2x. Here's sine of 3x. I've seen it compressed together even further. And if I think about how do the points move, what we'll see is each point on the red graph, if we divide by 3, we'll get to a point on the green graph, and we're dividing by 3 our x value. So this point right here on the maroon graph is at 90 degrees. Sine of 90 degrees would be 1 whole. And now where I get to my y value of 1 is not at 90 degrees, but it is at 1/3 of that, dividing by this factor 3. 90 divided by 3 takes me to right here, which is at 30 degrees. How about this point, and I'm referring to the one on the maroon, where we have a function value of 0 at 180 degrees. Now divide that 180 by 3 to get our value of 0 at 60 degrees. Let's just point out one more. Down here, -1 occurred at 270 degrees. 270 divided by this factor 3 means we'll see our first valley at 90 degrees. 270 divided by 3 equals 90. And there we see that function value of -1 at 90 degrees. We know that these trig graphs have this periodic repeating pattern to them, and we are interested in finding the period, which would be the distance it takes to complete one cycle. With cosine and sine, we talked about the period being 2 pi radians, or 360 degrees. That distance along the horizontal axis is what's required for us to see one complete cycle, and then we could see this piece being repeated over and over and over again. If we look at sine of 2x, which we know horizontally compressed this graph, it's going to change the period. So we're going to accomplish a complete cycle not in 360 degrees, but again divide by this factor 2. Now our period is 180 degrees. In between these 2 points, we see one complete circle. And if we're talking about radians, 2 pi radians divided by this 2 would be a period of 1 pi. So from before, we would talk about this B transformation, which is coefficient of x inside the function, as being a horizontal stretch or compress, and it still is, but now we're going to use terminology that's specific to trig functions, and we'll talk about the period. And the way it changes the period is if our full initial period is 2 pi, we divide 2 pi by the factor b. If we're talking degrees, it would be 360 degrees divided by b. Let's take one more look, this time at sine of 4x, to see if we can confirm that pattern. So one period of sine x is 360 degrees. 360 divided by 4 equals 90. So will we see one complete period in just 90 degrees? So in between these 2 points, there's 15, 30, 45, 60, 75, 90 degrees. So we're confirming this rule that you take your period, your initial period for sine and cosine, it's 2 pi, and we divide by this factor, this coefficient on x, the B transformation. Let's include a couple other things we know about the horizontal transformation, this B transformation. When our coefficient was a number greater than 1, our graph was squeezed, compressed together, and when we choose a number between 0 and 1, we do see this horizontal stretch, and everything is now it's still divided by 1/2, and basically divide by 1/2 is times 2. So we're stretching things out by a factor of 2. Our peak right here, which occurred at 90 degrees, now is occurring at 180 degrees after this multiply by 2. Right here, this intercept after 180 degrees, it's now intercepting after 360 degrees after the multiply by 2. And again, that's because we take those values and divide by the coefficient. Divide by 1/2 is why we're doing the multiply by 2. Multiplying the variable inside the function by -1 will accomplish another reflection. This time, it is a reflection on the y-axis. We see something similar from when we had our other reflection, that it was for us to see, actually, is this a vertical reflection or a horizontal reflection? And again, it's an idea that if we know that sine is an odd function, we'll know that reflecting horizontally leads to the exact same graph as reflecting vertically. So I want you to know that the rules from earlier transformations still apply, but with trig functions, we begin to see some effects that are coming from many different types of transformations, all leading to the same transformed graph. Our last transformation, the C transformation, is a constant added to the variable but still inside the function. This is going to be some sort of horizontal change, and since it's addition, it's going to be a horizontal shift to the left or to the right. And if you remember from function transformations earlier, adding a constant actually moves our graph, shifts it to the left, and subtracting a constant shifts our graph to the right. Those transformations working on the variable work opposite of what we would expect. Like our D transformation, when it was positive we shift up, when it's negative we shift down. That makes sense to me. But when we're addressing the variable inside the function, it works opposite. Add C, shift C units to the left. Subtract C, shift C units to the right. We're looking at our base function sine x in maroon, and in green we have a C transformation. We have added pi over 2. It's added, so we're looking for a shift to the left, and we do see that the graph in green is shifted left of the maroon graph, and by how many units? Pi over 2, that's 90 degrees. So I could see a shift of 30, 60, 90 degrees. Every point that I see on the maroon graph, if I shift it left by 90 degrees, I will land on the green graph. 30, 60, 90 degrees to the left. Something that's a little ambiguous here would be, well, could you say that I've shifted my graph to the right by 3 pi over 2, by 270 degrees? And I would say we can, with the algebra of these trig functions, show that it is true, that shifting to the left by pi over 2 is exactly the same as shifting to the right by 3 pi over 2. We'll get to that later, but now let's look at this shift in smaller increments to really see what sort of shift is happening. Here's pi over 10, adding in pi over 10, so we're just moving to the left a little bit. Pi over 9, so as we're increasing our value of C, we can see that we're moving this graph further and further to the left. So absolutely, when we see a constant added to the variable, we know that it is producing a shift. And a constant added will shift to the left, a constant subtracted will shift to the right. But as always with these trig functions, there are going to be a few possible transformations that lead to the graph, the transformed graph that we see. Here I'm attempting to illustrate shifting it by 2 pi. Now we know that 2 pi is our period, so if I shift it an entire period, I'm going to land on the exact same graph. Here is the result that we've seen a couple times now. We saw it from a reflection on the x-axis, we saw it from a reflection on the y-axis, and now we're showing it as a result of a shift, a horizontal shift. Plus pi, so you could say we've shifted it to the left by pi units 180 degrees, but it looks identical to a shift to the right of pi radians, or 180 degrees. Again, knowing the properties of these trig functions will show us that different transformations can lead to the same result. But we need to cover a very important detail about the horizontal shift. We're back to sine x and sine of x plus pi over 3, so we're shifted to the left by pi over 3 radians, or 60 degrees. If I focus on this point right here, this peak, and I go backward by 15, 30, 45, 60, okay, I land on the peak of the green. or if I look at these intercepts back to 15, 30, 45, 60. So definitely seeing this shift to the left of 60 degrees. But what if I decrease the period of these functions by going with sine of 2x and sine of 2x plus pi over 3? I'm still seeing that same value of c pi over 3, but what is the shift that we see here now? From the maroon graph, shift to the left only 15, 30 degrees this time. I can really see it with the intercepts. Shift to the left 15, 30 degrees. So something about changing this factor b is having an effect on our horizontal shift. Let's look at this a little bit further. Sine of 4x and sine of 4x plus pi over 3. Now our shift is only 1 unit by 15 degrees. Before, when we were first talking about the b transformation, we said it would shorten your period. Take your original period for sine, it was 2 pi, and divide by this factor, and it gives you your new period. Well, when it comes to our horizontal shift, this also must be divided by that factor, the b transformation, the b factor. In this example, pi over 3 divided by 4 would be pi over 12. That's 15 degrees, the exact 15 degree shift that we see in this example. Back to this one, pi over 3 divided by 2 would be pi over 6. That's 30 degrees, the shift we're seeing here. When it comes to describing what the effect of c is on a trigonometric function, we really have to be careful and work in that b is also going to have an effect on this horizontal shift. We could say that negative c over b is the phase shift. We saw that from the graphs that we would want to take this constant c and divide it by b to get the actual amount of the shift. And we also said that adding c would be a shift to the left. So if I want to talk about a shift to the right, this should be a negative c. The specific terminology we see with trig functions is the term phase shift. That's our horizontal shift. If the phase shift is positive, we say that's shifting to the right in the positive horizontal direction. And if the phase shift is negative, we're talking about shifting our graph to the left in the negative horizontal direction. So we account for this difference in signs by saying make it opposite of c over b. So if I see a plus, which I know is a shift to the left, this expression will give me a negative result. And when it comes to phase shift, negative means shifting to the left. If this was minus c, then this expression opposite of negative c over b would become positive. And minus c we know is shifting to the right, so this expression will give us a positive number for phase shift. So we know when we see a positive phase shift, that's shift to the right. So here's our structure where we see all 4 transformations in their spots. The a transformation multiplied to the function out front, d added, or if it's negative, subtracted from the function. B and c are working directly on the variable in the function. B is multiplying, c is added or subtracted if c was negative. And let's talk about an example that you would have to handle. Given this function, we want to come up with the amplitude, the period, and the phase shift. So remember that our a transformation is the amplitude, the number right out front. I can see it readily. I see it negative 1.5, but amplitude, since it's a distance, we always use a positive number. You could say absolute value of a should be our amplitude. So we'll go with a positive 1.5 for the amplitude. It's just bad form to use a negative number for amplitude. We want to recognize that quantity is always considered to be positive. Next, the period. We know that we look at the b transformation for the period, but we need to do 2 pi divided by that number. 2 pi divided by 3 is our new period. Remember, by default we start at 2 pi if we're dealing with a sine function, and dividing by b gets us to our new period, 2 pi over 3. The phase shift, we're looking at this pi over 2, and we have to divide that by b as well. Pi over 2 divided by 3 would be pi over 6, and it's a negative in here, which we know is shifting to the right, so we want to come up with a positive phase shift, positive pi over 6. And thinking about use that expression negative c over b, that would also lead to this result of a positive pi over 6. Now let's look at the graphs. We're going to talk about how you might come up with, if you had to make some graphs by hand, how would you graph this function right here? Now we have access to tons of calculators and computers that make graphs for us, so I'm not going into tremendous detail here. But basically, you start with the base function. So I make my graph of sine. We know how to do that based on some main increments on the unit circle and those ordered pairs. Now, one by one, I'll introduce these transformations. The first one I'm going to do is the B transformation. I'm going to change the period. I know that this was a sine of 3x. Now I'm ignoring the negative 1.5 out front. I'm ignoring the plus 1 and the minus pi over 2. I'm just doing transformations one at a time. So the one I'm doing right now is coming up with sine of 3x. Doing this by hand, every point that I see on maroon, I'm dividing my x value by 3. So a peak at 90 degrees divided by 3 is now at 30 degrees. The intercept at 180 divided by 3 is now at 60 degrees, and so on. I pick a few points, I scale each one of them back by a third to produce gradually the graph in green. So I've got sine of 3x that way. Next transformation will be the A transformation. I'll multiply by negative 1.5. Since we're multiplying by a negative, I have to do two things. Not only stretch by 1.5, but also reflect on the x-axis. So basically, any point that I have above, it's going to get swapped down below, and at the same time I'm going to increase by a factor of 1.5. So our valley down here at negative 1 is now a peak, and stretched out to 1.5. The peaks at positive 1 have now been flipped down and stretched down to negative 1.5. That's how I'm coming up with the graph of negative 1.5 times sine of 3x. Next, I'll work in the phase shift. True, we had 3x minus pi over 2 in parentheses, but I know that I do c over b to get that actual phase shift, pi over 6. And we had a positive, so we're shifting to the right. Pi over 6 is 30 degrees, so there's our 30 degrees. Got that going on all over. Wherever we see a point in purple, we shift it to the right by 30 degrees. There's our graph of negative 1.5 times sine of 3x minus pi over 2. We only have one transformation left, the plus 1 at the end, and that's our vertical shift. So every point is now being shifted up one full unit. Where my peaks are at 1.5, now they're at 2.5. The valleys, which were at negative 1.5, have been shifted up 1 to negative 0.5. And my intercepts here at 0 now are seen here on this line at positive 1. So every point picked up and moved up 1 unit, and there's our final graph, including all of those transformations. Let's do another example. First, the amplitude. Okay, that's the gimme. It's this number out front, so our amplitude 2.4. Next, the period. We know 2 pi, because it's cosine, start off with 2 pi. 2 pi divided by 1/2. We remember this 1/2 is actually doing a horizontal stretch, and the 2 pi divided by 1/2 is 2 pi times 2. 4 pi is our new period. And lastly, the phase shift, c divided by b, and flip signs, pi over 6 divided by 1/2. So again, that's times 2. That's going to lead us to a positive pi over 3. And let's go through the steps of coming up with this transformed graph as well. Now we're starting with cosine function. Let's do the change in period first. So look at cosine of 1/2 x. And we get there by a horizontal stretch. Everything is now moved twice as far away from the y-axis as it was. This point right here at the intercept, instead of being at 90, now it's at 180. This valley down here at 180, now it's at 360, and so on. Everything has been stretched by a factor of 2. The next transformation I'll do is going to be the vertical stretch, the times 2.4. So every peak used to be at 1, now they're going to be up at 2.4. All the valleys from negative 1 are going to be pulled down to negative 2.4. Next transformation will be, well, we only have one left in this example. We had inside the cosine, 1/2 x minus pi over 6, we did the math and showed that it's a phase shift of a positive pi over 3. That's 60 degrees. So I'm going to take this last graph and shift every point to the right by 60 degrees, and there's our final transformed graph. Last example, just to touch on tangent one more time. Amplitude is not really used in the context of tangent functions. That's really more so for those wave functions, sine or cosine. So we'll skip amplitude. Phase shift as well, not really used so much with tangent functions, but at period is really the one that I'd like to make a point out of anyways. So we're only going to talk about period for the tangent function. We know that we look for this coefficient on x, but we start with our initial period and divide by this number. And I wanted to point this out because what is period of a tangent function, tangent of x? It's not 2 pi, it's just 1 pi. So in this example, we'll take our starting period, which is just 1 pi for a tangent function. We still divide by the coefficient of x. It gives us a new period of pi over 2. And let's look at this graph. Start with the base function tangent of x. Now we'll change the period. Graph the function tangent of 2x. So every point that I see is now being brought half as far from the y-axis. Instead of this point out here being at 180 degrees, now it's divided by 2 back here at 90 degrees, and so on. So here's our graph of tangent 2x. Our period has now been shortened from 180 degrees down to 90 degrees, or pi over 2 radians. Next, we did have a horizontal shift adding pi over 2. And it's working the same way, where we have to really think about that constant c divided by b. So a shift in this case, it's not pi over 2. Pi over 2 divided by 2, or pi over 4, which is 45 degrees. So our shift, horizontal shift, we can now see it's 15, 30, 45 degrees. We can't tell if it's to the left or to the right, but our phase shift, what we know about horizontal shift, tells us that this is actually a shift to the left. We're adding in pi over 2, that is a shift to the left. So there is our final function incorporating those two transformations, and we're cautious about using the period that we know. We start off with a period of 2 pi for cosine and sine, but a period of just 1 pi for tangent. Let's do a quick recap of these transformations. A was the amplitude, and left over from our original thoughts of function transformations, what we know about A is that it will do a vertical stretch when A is bigger than 1. It will do a vertical compress when A is between 0 and 1. And if we have a negative A, it's also going to reflect on the x-axis. This B parameter is some sort of horizontal stretch or compress. It's a horizontal stretch for numbers between 0 and 1. It's a horizontal compress once we deal with numbers greater than 1. And if we end up with a negative value of b, it's also going to do a reflection on the y-axis. In terms of our period, we would find period by doing 2 pi divided by b, but we would only do that for sine and cosine, which start out with a period of 2 pi. For tangent, it would be 1 pi divided by b. Now the C transformation, we said that to really see what the horizontal shift, what that phase shift would be, we had to do C divided by B. And I'm going to show you now, algebraically, why that is. The C transformation, the constant added to the variable, is really not shown right here. We're actually adding C not to x, but to this product B times x. If we want to really illustrate what is being added only to the variable, the way to do that is to factor this b off of the x. So we're going to bring a b outside with x in parentheses, x plus some quantity. And remember, when we factor out a common factor, it's because we're dividing it out. I've divided b out from the bx, leaving behind just the x. If I divide b out from c, I don't know what those numbers are. I can't tell you what it's going to divide to equal. All I can do is call it c over b. That's me dividing the b out and putting it out front, but it's going to leave behind a c over b. And if I think quickly about doing a distribute, it will definitely take me back to bx plus c. So now we're actually seeing this quantity that is added to the variable. And this is why we need to do c divided by b to really understand what our horizontal shift is. And also, I have a plus c included here, but we'll want to know that a plus c means shift to the left, a minus c means shift to the right. So left if we're dealing with a positive c over b, right if we're dealing with a negative c over b. But if we're talking about phase shift, I would say find your phase shift by doing a negative c over b, because we would like phase shift to be positive when we represent shifting to the right, and phase shift is negative when we represent a shift to the left. Last one is D. D is a pretty simple one. It's the vertical shift, shifting it up when D is positive, shifting it down when D is negative. So knowing these transformations take on a little bit of additional significance with these trig graphs, especially talking about amplitude, period, and phase shift.